chain of events, cause and effect. We analyse what went right and what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is entirely supported by you, our listeners. If you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. Premium support is available via Patreon, through the Apple Podcasts channel subscription, and through Spotify. Premium supporters have access to high-quality versions of episodes, as well as bonus material from all of our shows not available anywhere else. Causality is also a Podcasting 2.0 enhanced show with value support and a new listener-submitted soundbite option if you'd like to participate. Just visit engineer.network/causality to learn how you can help this show to continue to be made. Thank you. Hyatt Regency, Kansas City. Construction of the 40-story high Hyatt Regency Hotel in Kansas City, Missouri began in May of 1978, and it opened its doors to the public on the 1st of July 1980 and remained the tallest building in Missouri until 1986. The hotel was situated in the Crown Center commercial complex, which was part of an urban revitalization of an older part of Kansas City near Union Station. The hotel had a revolving restaurant, an exhibit hall, conference facilities, and more than 700 guest rooms. One of the other widely publicized features of the new hotel was its multi-story atrium, which had 3 walkways, each at a different floor level, each suspended from the ceiling above. The atrium is a large open area, approximately 36 meters, that's 117 feet deep, 44 meters or 145 feet wide, and 15 meters or 50 feet high, containing a bar, a stage, and a large open space that would sometimes be used as a dance floor. Each walkway was 47 meters, that's 121 feet long, and was constructed from steel, concrete, and glass, weighing in at approximately 29 tons or 64,000 pounds each. The hotel itself was split into 2 sections, a high-rise section and a function or events block, connected by the atrium. Walkways connected those 2 sections on levels 2, 3, and 4, with level 3 offset from 2 and 4, such that levels 2 and 4 walkways were directly above and below each other, adjacent to the outside wall, with level 3 independently suspended and adjacent to the others, closer to the center of the atrium. The Hyatt Regency Hotel regularly hosted a Friday night tea dance with live music and dance competitions. A tea dance is a European tradition, though also called the dansante, or dancing tea in French, was a dance held in the summer or early autumn, late afternoons before sunset. With that background, let's talk about the incident itself. On Friday evening, the 17th of July 1981, the Hyatt Regency Hotel atrium was once again hosting a regular tea dance, with live music, that evening played by the Steve Miller Orchestra. The dance was scheduled to go for 3 hours in total, starting at 5 p.m. and finishing by 8 p.m., playing a variety of jazz swing music. At 3 p.m. local time, the first people started arriving, and within 90 minutes, the first floor of the atrium was now fully occupied, forcing people to move to the atrium terrace and walkways before the official start at 5 p.m. By 7 p.m., the crowd was estimated at between 1,500 and 2,000 people in the entire atrium area. At 7:04 p.m., the band returned and began playing as part of the dance competition. At approximately 7:05 p.m., the 4th floor walkway, with an estimated 20 people standing on it, buckled in the center and began to fall onto the 2nd floor walkway directly beneath it. As the falling walkway impacted the 2nd floor walkway, with approximately 40 people on it, the 2nd walkway then also collapsed, with both walkways collapsing onto the ground beneath, near a very crowded area adjacent to the bar. The number of people on the walkways has been impossible to determine with any certainty, as the television crew covering the event were changing batteries in their equipment when the collapse occurred. Water pipes were severed in the collapse and electrical cables were dislodged, leaving the lobby in near darkness, with frequent sparks from arcing electrical equipment intermittently lighting the atrium. It took 3 minutes for the Kansas City Fire Department to be contacted in the confusion, followed by the police department shortly thereafter. By 7:18 p.m., a total of 7 ambulances had arrived at the hotel. By 7:52 p.m., an estimated 100 firefighters and emergency workers were now actively involved in rescuing people from the wreckage. Due to the weight of the walkways, heavy cranes were brought in to remove the debris, with the first walkway removed by 3:15 a.m. the following morning. The last survivor was pulled from the debris at approximately 4:30 a.m. 114 people were killed, and 216 were injured. It remains the deadliest unintentional structural collapse in the history of the United States. Let's talk about the investigations. Yes, there were multiple. The mayor of Kansas City, Richard L. Berkeley, formally requested the National Bureau of Standards to independently investigate the most probable cause of the Walkway collapse. Their 378-page report examines in great detail the physics behind the failure and makes for interesting reading. In 1983, a grand jury was convened in Kansas City to investigate if the collapse was as a result of any illegal actions of those involved. In 1984, the state of Missouri convened an administrative hearing to determine whether there had been any violation of state licensing laws by those involved. In 1985, the ASCE, that's the American Society of Civil Engineers, also held a disciplinary hearing. The relevant findings from all of these will be discussed in due course. But before we get to that, let's talk a little bit about the construction of the hotel. The hotel was built in the late 1970s when there was a period of high inflation, high interest rates, and high unemployment. The number of available construction projects at that time was limited, and hence the contracting companies at that time priced very aggressively to win work so that they could stay in business. As projects increased in availability, those same companies then pushed to close out their projects they had on the books so they could start on the next project as soon as they could. This era of construction also saw the popularization of the so-called fast-track method of design and construction. Projects delivered by fast-track are characterized by construction leading ahead of the final completed design, and, in the context of civil engineering specifically, structural design precedes architectural's final design. There's reliance on conceptual sketches, preliminary drawings, and early component orders with redlining of shop drawings and multiple reissues of design drawings during the construction phase. Sounds risky? Well, if you have good quality assurance, it can still work, and on large projects can reduce the time taken to deliver a project by 25%, with the trade-off of increased cost overall in many cases. Sometimes time is money too, so the sooner it's built, the sooner it can make income, and those trade-offs are considered to be worth it in the end. So for this hotel construction, who were the players involved? There were a few. Eldridge & Son Construction Company was the general contractor on the project. Eldridge subcontracted the steelwork fabrication to Havens Steel Company as the fabricator in December 1978. Gillum Colico Structural Engineering Consultants Incorporated, or GCE, was selected to perform all structural engineering services for the design and construction of the hotel in July of 1976. Jack Gillum was one of the principals of GCE. GCE subcontracted all structural engineering services for the project to Jack D. Gillum and Associates Limited, and designated Jack Gillum as the professional engineer for the project, noting that Jack Gillum was also the president of that firm, and hence he was the engineer of record. Jack Gillum appointed Daniel Duncan from Jack D. Gillum and Associates as well as the project manager for daily work execution, as well as a project engineer and a senior project designer in late 1976, along with a full project team. Patty, Birkbile and Nelson, Herbert Duncan and Monroe Lefbrever, Architects Planners Consortium Incorporated, or PBNDML for short, served as associate architects, and during 1977 developed the basic design and some of the detailed designs for different parts of the hotel. In June of 1978, Jack D. Gillum and Associates lost both the Hyatt Regency Hotel's project's project engineer and its senior project designer in very quick succession, leaving only the project manager, Daniel Duncan, with any history of the design decisions that had been made to date. During the construction phase of the hotel, there was an incident regarding the atrium. On Sunday the 14th of October 1979, during construction, a section of the east atrium roof on the north side of the building, above the restaurant area, fell 4 stories onto the lobby floor. Fortunately, it happened on a Sunday when no one was working on site, and hence there were no injuries. A spokesman for the Crown Center Redevelopment Corporation, the then owner of the hotel under construction, stated that and I quote, "beam fell because of an installation problem," end quote. Following the incident, it came to light that the general contractor, Eldridge & Son, was fined $5,920 for 17 violations during the hotel's construction. Having said that, none of these issues were related directly to the collapse, however, are suggestive of a fast-paced construction process with an inadequate amount of quality assurance. There's quite a lengthy analysis of this specific incident in the show notes by Gregory Luth, The Chronology of Hyatt Regency Collapse, if you're interested. The key point is that the so-called installation problem was actually more of a lack of a cohesive design problem that during installation was worked around rather than questioned and fixed properly. Had the designers taken that opportunity to stop the job and review the design from end to end, they would have more than likely uncovered the walkway design issues we're about to go through. But they didn't. Let's talk about the walkway design. The walkway is comprised of 4 spans in total, with each span denoted by its interconnecting joints and hanging rods starting at 7 through to 11. Hence, the first span is designated span 7-8, then 8-9, 9-10, and 10-11. Before you wonder why the numbering starts at 7, the numbers line up with the building's column numbers, hence the walkways hung between columns 7 and 11 of the overall building space. Because the walkways on levels 2 and 4 were joined together by hanging rods, the 4th floor walkway was referred to as upper and the 2nd floor as lower. Finally, the hanging rods were positioned on either the east or west side of the walkway. For example, the eastern centermost rod connection point on the 4th floor was denoted 9UE. The box girders connecting the walkway to the hanger rods were made of 200mm wide, that's 8 inches, of C-channel welded together along their length, hence creating the so-called box. How heavy was it though? Because during the investigation, they found significant variability in the thickness of the concrete decking and topping materials, so they confirmed the final weights by weighing several walkway spans, as the design drawings did not align to what was constructed in that regard. Analysing the fallen walkway sections led to an estimate of the mass of the walkway to within a worst-case error of plus or minus 136 kilograms or 300 pounds. The addition of gypsum board to meet fire endurance requirements added approximately 1,050 kilograms, that's 2,310 pounds, to each walkway span. We'll get to that shortly. The investigators therefore concluded that the average final weight of a single walkway span as built was 8,050 kilograms, that's 17,750 pounds, which exceeded the as-designed span weight by about 8%. Not a good start. So what went wrong? We know that the walkways were 8% heavier than their design, but that's only one issue. It was determined that the most likely connection point that failed first was 9UE, with transferred load to spans U8-9 and U9-10 on the east connections, then causing 8UE and 10UE to rapidly fail, with the other side of the walkway's joint, 9UW, failing as well. The method of failure was that the nut and washer pulled through the center of the box beam under high load. Given the construction method of welding 2 C-channels together, the investigators spent significant time confirming that the quality of the welding job on those channels was not a factor in the incident. In addition, whilst there were people present on the walkways, it was found in the investigation that the mass of the people on the walkways was not a significant contributing factor to the failure that they saw in the incident. The 2 centermost spans then rotated downwards, pulling span U10-11 off its bearing seats at the building column number 11. As the upper walkway then fell onto the lower walkway, it followed a similar failure progression. The investigation determined that there were 2 design changes that contributed to this incident, as well as a design gap. We'll talk about each in turn. The first, fireproofing in March 1978. A routine design review by the Codes Administration Office, Kansas City Public Works Department, resulted in a 6-page handwritten assessment of the fire endurance of the walkway's structural steel, dated the 10th of March 1978. A meeting was held on the 16th of March 1978 between representatives of the Codes Administration Office and the architects PBN-DML, with 2 pages of minutes, which included an agreement to clad the walkway structural steel with gypsum board to address fire resilience concerns. Specifically, 2 layers of 16mm, that's 5/8 of an inch thick, gypsum board, supported by 0.8mm metal studs and nailing strips, then attached to the structural steel by power-driven fasteners. The structural drawings were reissued on the 30th of March 1978, and it is unclear in the documentation at the time if any changes were made to the structural details as a result of gypsum board being added to each walkway span. The investigation concluded that the walkway design did not get adjusted to account for the additional load from retrofitting gypsum board as a fire-retardant material during design. That said, they also concluded that even if the load from the gypsum board wasn't present, there would still have been insufficient redundancy, also called reserve load capacity, in the hanger rod design to resist the failure of a single rod. Hence, if one breaks, they'll all break. The second design change, also in March 1978, related to the hanger rod connection. In March 1978, drawings for the walkway hanger showed a single rod continuously threaded from top to bottom that was suspended from the beams on the atrium ceiling, passing through the 4th floor walkway and 2nd floor box beams with securing nuts and washers at each walkway level. In early January 1979, the drawings were now at the fabricators, Haven Steel Company, and their engineering manager called the structural engineer's project manager. Haven's engineering manager raised concerns about the durability of a continuously threaded rod over that length during construction. The original design called for a nut 6.1 meters up the hanger rod and didn't use sleeve nuts. That, coupled with the higher cost of manufacture, they proposed to change the design from a single continuous rod to 2 rods instead, with threads on each end. According to Haven's testimony, the structural engineer checked the turning moment and the shear force presented at the box beam for the offset condition while on the phone, and Daniel Duncan accepted that change over the phone. The structural engineer then asked the fabricator to submit the change request through the normal channels for approval. The shop drawings were then marked up to now have 2 hanger rods with a 102mm, that's a 4-inch inset, at the 4th floor walkway connection point in place of the original single continuous hanger rod arrangement. To put it another way, the ceiling to upper walkway rods were on the outside, and the upper to lower walkway rods were offset on the inside of those. On the 12th of January 1979, Haven Steel Company pulled the Hyatt Regency project out of their engineering department and then subcontracted the full construction drafting of the partially completed shop drawings to an external engineering firm. This was due to Haven's winning a large project, and they required their engineering resources to be focused on the new job instead. The outsourced drawings included the box beam detail, but no rod connection was shown in its detail, which unfortunately is common practice in the industry. Different drawings show different details based on their final intended use cases. To understand the overall design of the connection configuration to the box beams, a person would need to consider all of the drawings and specifications collectively, not individually. The offset rod design change was therefore never submitted for a formal review in its entirety, and the final connection to the box beams was only implied on the shop drawings. They assumed that the connection design was complete and specified elsewhere, so they simply added the weld symbol at the connection point before sending the drawings out for final approval. Ordinarily, if there are any design changes required to the shop drawings, they would be submitted under a separate cover sheet, along with a request for engineering validation of the shop drawings. This did not occur. On the 7th of February, the outside detailer made their final consistency and completeness checks, and the drawings were sent to the structural engineer for engineering approval. With various communication delays, the drawings didn't reach the engineer's desk until Thursday, the 16th of February, and the contractor had requested expedited approval due to the construction timetable pressures under the contract. At that time, both the project engineer and designer had long since departed, and the project manager, Daniel Duncan, was too short of time to review the drawings himself, so he delegated their checking to a senior technician. The senior technician was trained in structural engineering and had 2 decades of experience, but wasn't licensed as an engineer. Whilst he queried about the rod specification, more on that in a moment, there were no other significant findings, and the drawings were returned approved for construction on Sunday, the 27th of February. That's right, they were working the Sunday to get it done. This modification essentially doubled the load transferred from the 4th floor walkway box beam to the holding nut for the upper hanging rod from 91 kilonewtons to 181 kilonewtons. Another way to describe this is the nut holding the weight of the fourth floor walkway in the original design only had the weight of its own floor in that segment applied to it with a continuous rod. Once a second rod was added, instead of the load from the lower walkway being transferred up through the rod to the ceiling, since it was hanging from the upper walkway now, not a common rod, the entire mass of the lower walkway segment was applied to the upper walkway as well. Therefore, the mass on the holding nut on the fourth floor walkway was effectively doubled. Having said all of that, with the correct redundancy factors applied and under the original design, accounting for the correct weight of the walkways as they were built, the minimum load value needed to be 151 kilonewtons even with a single rod design, and this still didn't meet the AISC, that's the American Institute of Steel Construction, specifications requirements. Specifically, the AISC specification for design, fabrication, and erection of structural steel for buildings, as well as the Code of Standard Practice for steel buildings and bridges, as required by the Kansas City Building Code. Another key problem was the design of the walkway support beam's connection to the hanger rod. The original design sketch for the rod connection showed a bracket extending off of the web of the W8, that's a wide flange I-beam. W8, that's the vertical section of the beam, where 8 in W8 is the height of that beam in inches. And that had an indicative spacing for the rod connection, with the rod sizing and forces all drawn on the engineer's sketch. In March 1978, the project manager replaced the W8 beam at the hanger location with a pair of 8-inch channels we previously spoke about, turned toe-to-toe, and extended these past the interconnecting W16 beam. This was done to eliminate concerns about the eccentricity of the original suggested bracket connection with the I-beam. The revised design was, in effect, symmetrical, where the original design wasn't. The revised engineer's sketch also showed the rod size, force, and rod grade. When the draftsman transcribed the engineer's sketch to a for-construction drawing, they omitted the note specifying the strength of a 413 megapascal or 60 kips for the hanger rods. In civil engineering in that era, writing the load detail on the sketch indicated to the fabricator that the connection design still needed to be completed, and this was normally part of the fabricator's scope of work. The engineer had assumed that the fabricator would complete the design detail for the connection to the box beam hanger. It is not clear why the additional details were not transcribed by the draftsman. However, the fact that they weren't led to a misassumption by the fabricator about whether the connection design was actually complete. They believed it was when it wasn't, and equally the engineer believed it was being handled by the fabricator when it wasn't. Placing the rod through the weak point of the welded C channels may have looked the most pleasant to the eye. However, the nature of C channels is that they taper from each corner to each tip furthest from the back of the C, such that the tips are the narrowest parts of the channel. Placing those tip to tip and then running a weld seam along them to join them together, and then grinding that weld flat for assembly, resulted in a very weak connection. The welders on site recognized this and attempted to weld the inner join line inside the box section, but they could only reach as far in as the end of their welding rod allowed them to. Hardly precision work and pretty much unconstructible in that way, laws of physics and all that. A final note, though, about the rod design change that also occurred in March 1978. So the architect requested the rods be changed from 44.5 millimeters, that's 1 3/4 inch, to 32 millimeters, or 1 1/4 inch, to lighten up the appearance of the bridges. The original drawing showing the rod detail did not specify the material on the drawing, though the other specifications suggested standard A36 grade rods, that's 36 KSI tensile strength, should be used based on the original design. To achieve the load-bearing requirements for the narrower rod, a grade 60 rod, therefore with a 60 KSI tensile strength, would be required, and this was marked up on the revised engineer's sketch. Just a quick note, I talk about minimum yield strength. That's the amount of stress a material can withstand before it succumbs to a permanent deformation and doesn't return back to where it started. In imperial units, it's usually expressed in KSI, which is kilopounds per square inch of pressure. Metric units is formally in MPa, or megapascals of pressure. If you recall, the final drafting for the construction drawing set was outsourced by the fabricator to another engineering firm that had a long-standing business relationship with the fabricator. During the course of checking the drawings, the technician from the outsourced back-drafting company involved asked the project manager about the strength of the hanger rods. The technician's own calculations found that 36 KSI steel rod would not fully support the load indicated on the other available drawings. The project manager responded from memory that it was a high-strength rod. However, no mention of the specific rod grade was provided. Further than that, no attempt was made to verify this by looking at a complete set of drawings and specifications, and the drawings were issued without this information detailed on the construction drawing set. Some analyses of this incident call this out as a cause of the incident, but that's not really true, as the rods themselves didn't actually fail. Having said that, I have no doubt at all that had the box beam joints not failed first, with the passage of enough time and cumulative deformation of the rods eventually would have led to a collapse in the future. When exactly that could have happened, who can say? Technically not a cause of this incident, but clearly an error that could have led to a different incident had the other issues not beaten them to it first. Let's talk a little bit about the legal fallout. In 1984, Missouri's Board of Architects, Professional Engineers, and Land Surveyors commenced disciplinary proceedings against Duncan, Gillum, and GCE. After a 27-day hearing and weeks of compiling their report, the Commission eventually issued its findings, which were 442 pages long, and found all three parties grossly negligent and revoked their licenses. Judge James B. Dush, an administrative law judge for Missouri's Administrative Hearing Commission, found the structural engineers guilty of gross negligence, misconduct, and unprofessional conduct. They claimed that the design flaws had resulted from a miscommunication between Jack D. Gillum and Associates and the Haven Steel Company. Mr. Duncan, Mr. Gillum, and GCE unsuccessfully appealed their decision up to the Missouri Court of Appeals. The Court of Appeals also rejected the more substantive attacks on the sufficiency of the evidence in the initial proceedings, stating the following. 1. And I quote, Mr. Duncan was responsible for designing and approving the building structure, of which the walkways fell within that scope. The walkways offered a potential of great danger to human life if defectively designed. Point 2. Mr. Duncan approved the fabricator's change, recommending it to the architect, and approved shop drawings reflecting it without confirming its acceptability, noting that the change effectively doubled the box connection load. And 3. Mr. Duncan never reviewed the shop drawings, even though such a review is an engineering function that even GCE's in-house policies required that he do. End quote. The Court of Appeals upheld the original conclusion that, and I quote, the conduct of Duncan from initial design through shop drawing review and through the subsequent requested connection review supports the Commission's finding of conscious indifference to non-delegatable professional duty. End quote. The Court of Appeal also upheld the original conclusion that Mr. Gillum had displayed gross negligence because he failed as the engineer of record, and I quote, to assure that the Hyatt engineering designs and drawings were structurally sound prior to impressing thereupon his seal, and failed to assure adequate shop drawing review. End quote. During the trial, the detailer, architect, fabricator, and technician all testified that during construction they had contacted the project engineer regarding the structural integrity of the walkway connection detail. They claimed that each time it was raised, the project engineer assured them that the connection design was sound, and whilst he claimed to have checked the detail, in reality there was no evidence found that he had ever performed any calculations at all. The legal repercussions for the Hyatt engineers firmly established the engineer of record's responsibilities for the structural integrity of an entire building during construction, including the shop drawings. Hence, in the civil engineering context, the engineer of record should design and detail all non-standard structural connections. More broadly, all new designs need to be thoroughly checked, and all modifications to design details require a formal written approval from the engineer of record. The day before that decision was handed down by Judge Dosh, the American Society of Civil Engineers had announced a new policy of holding structural engineers responsible for all elements of structural safety in the buildings they design. Let's talk about the aftermath. The hotel reopened 3 months after the incident, after $5 million of reconstruction. A single walkway was reinstalled, only this time supported from beneath by concrete pillars. Other than the third floor now being left without a connecting walkway, the lobby generally retained its original design. The hotel was renamed the Hyatt Regency Crown Centre in 1987, but when Starwood took over the hotel in November of 2011, it was renamed the Sheraton Kansas City Hotel at Crown Centre. Mr. Gillum and Mr. Duncan had their engineering licenses revoked, as did the company GCE, and the two had their memberships to the ASCE revoked as well. GCE survived only by merging with a Denver engineering firm, Ketchum, Conkle, Nickel, Barrett. No criminal charges were filed, and no one was prosecuted. Compensation claims from the courts awarded victims around $140 million paid by the Crown Centre Redevelopment Corporation, the owner of the hotel, with multiple significant insurance payouts on top of that. In 2015, over 3 decades later, a memorial was finally built adjacent to the hotel and was paid for by the Skywalk Memorial Foundation. It had taken the foundation a decade to raise the $550,000 to pay for the memorial and associated maintenance endowment. The names of each of the victims are etched in the memorial, of which the centerpiece is a 6-meter or 20 feet high abstract sculpture of a couple embraced as they dance. So what do we learn from all this? There are 3 points I'd like to go over here. Responsibility of the engineers during design, complete design reviews rather than piecemeal, and personnel churn. The engineer of record is a commonly used term in North America, which has, in the past and particularly prior to this incident, had varying interpretations as the ultimate responsibility of that job role in a construction project. The Hyatt Regency Walkway collapse has become the legal precedent against which the role of EOR has ever since been defined in the USA. The buck stops with the engineer of record. They are responsible. In Australia, we have legal requirements under the Professional Engineers Act, and for many engineering disciplines today, if you aren't a registered professional engineer in the state you're operating in and/or a chartered professional engineer in Australia, then you aren't allowed to sign off on a design drawing. I've been an RPEQ in electrical engineering for 17 years, and also an RPEQ in ITEE and a chartered professional engineer in both as well, and I take those responsibilities extremely seriously. When I stamp and sign a drawing, it means I've checked every detail of that drawing to the best of my ability, which is in effect what the engineer of record is required to do as well. When I'm asked to RPEQ a drawing, there's also additional requirements. I need to have been involved with the design from start to finish, an aspect that was lacking in the case of this specific incident. I've been involved in projects where we've spent significant amounts of money subcontracting to find the right RPEQ from other organizations in order to get the design correctly validated after that specific engineer had left the design organization mid-project. We tracked them down to their new job, and we got them back. Design reviews for complex systems aren't as simple as you'd like sometimes, especially when we fractionalize our designs. I like to call it fractional engineering. The idea that reviewing the design or change as a whole just takes too long or has too many hurdles when it's considered in its entirety. So we break it into fractions of the whole and review those, one fraction or one slice at a time in isolation. There's often too much detail to put on a single drawing or in a single specification, which means the engineer needs to often read, ingest, and comprehend a significant number of drawings and information in order to determine if the design, in its entirety, is safe and correct. That takes more time, and as they say, it takes as long as it takes if you have to do it right. The time pressures and distractions from other elements of the building's construction clearly affected the outcome in this incident. It's just a walkway. I have bigger concerns. I have no doubt that kind of mindset was a factor. Finally, though, personnel churn. It's insidious, and it comes from a belief that people can be plug and play. We're all just numbers. I've worked for companies that push hard on documenting everything, turning everything into a process with evidence provided for every single step, and then when someone leaves the organization, the management layer hire someone new and think everything can just pick up from where it was. No risk, no problem, Thinking is, any new person can just read all the documents, comprehend the design, and finish the job. If only it worked that way. It is simply not possible to write down every last detail, every conversation, every side note, every corridor conversation, site meeting, inspection note, and even if it was, could the next person that wasn't present early in the project then absorb all of that information and comprehend its importance and context in any reasonable amount of time, enough to finish the job without an incident? It's complete fiction. We are not plug and play. We are the sum of our experiences, and we are unique. So few things in engineering are truly copy and paste widgets, and even if they are, the larger the scale, the differences location and materials makes can vastly impact the outcome. It's so important to keep the core team consistent in projects, and if that means paying more, giving people what they want to get them to stay, that's not pandering. That's a long-term vision about what's the best for the project and the company overall, and that's what it means to be a good manager. Not trying the sell of plug and play, we'll roll on, it'll be fine. That's not management. Building and maintaining a good, stable, competent team that communicates well together makes an enormous difference. Creating time and space to execute thorough design reviews does too. Somewhat of an unusual footnote, however. When something traumatic like this occurs to a person, they can handle it in a multitude of ways. We saw the tragedy of the Challenger space shuttle engineers, with Bob Ebling retiring from engineering, unable to practice, consumed by guilt, although admittedly he didn't cause the Challenger explosion, but he did fail to stop the launch. But in this case, something altogether different happened. Jack Gillam was born on the 21st of November 1928 and graduated from the University of Kansas with a degree in architectural engineering, before being drafted into the Army to serve in the Korean War between 1950 and 1952. In the early 1960s, he found his own structural engineering company, Jack D. Gillam and Associates, and was known for many prominent engineering designs around the world, until Hyatt Regency. Whilst he initially fought the allegations against him, he ultimately came to a different conclusion about his involvement and accepted that he was, in fact, partly to blame for the incident. As he lost his engineering license, he instead decided to spend the rest of his working career advising, teaching, and publicly speaking about how he and his company had got it wrong and how we can all learn from it. He wrote multiple papers, including the excellent The Engineer of Record and Design Responsibility paper that's linked in the show notes. He passed away on the 4th of July 2012, aged 83 years old. I've gone a bit back and forth on how I feel about him, but in the end, Jack Gillam could have gone into seclusion, racked by guilt, but he chose to stay out in front and essentially do exactly what I'm doing here, with causality. He tried to educate people about how it can go wrong, as it had for him personally in his case, to try and prevent future incidents from occurring. And that, on balance, I think that was the right call to make. And I'm glad he chose that in the end over alternatives. At the risk of being a touch bit flippant, the old and mostly untraceable saying is, when you assume, you make an ass out of you and me. The fast-track method of construction employed here led engineers and fabricators leaning on assumptions out of a lack of available time, with horrible results. For those engineers listening to this now, whether you're reviewing a design, even if you're not the EOR or your CPeng or RPeng aren't on the line, take that review with the same level of vigor as if they were. Gather the information you need to be sure if the design isn't clear and push back. If you need more time, you need more time. If you need to speak with the original designer, find them. Ask them. Get clarity. Get it right. Being an engineer can be a stressful job, but can also be a rewarding one too. I regularly think back over my 25-year career to date, and I wonder if someday an error I made in the past might turn out with negative consequences, ones that I didn't foresee at the time in the past. I try not to dwell on it, but that's not really the point. I use those thoughts, those fears, to keep me sharp. A bit of fear isn't a bad thing. It's a reminder to take what I do, what many of us do for a living, very, very seriously. Had the structural engineers and fabricators done the same on this project, those 114 people might not have died. Make the time. Do better. If you're enjoying Causality and you'd like to support us and keep the show ad-free, you can by becoming a premium supporter. Premium support is available via Patreon, through the Apple Podcasts channel subscription, and through Spotify. Just visit engineered.network/causality to learn how you can help this show to continue to be made. Thank you. A big thank you to all of our supporters. A special thank you to our silver producers, Mitch Bielger, Kevin Kosh, Leslie, Shane O'Neill, Hafthor, Jared, Bill, Joel Marr, Katarina Will, and Dave Jones. And an extra special thank you to both of our gold producers, Stephen Bridle, and our gold producer known only as R. Causality is heavily researched, and links to all materials used for the creation of this episode are contained in the show notes. You can find them in the text of the episode description of your podcast player or on our website. Causality is a Podcasting 2.0 enhanced show, and with the right podcast player, you'll have episode locations, enhanced chapters, and real-time subtitles on selected episodes. And you can also stream Satoshis and boost with a message if you like. There's details on how, along with the Boostergram leaderboard on our website. Causality now has support for listener-submitted sound bites from any episode. You can create and email in for inclusion on the website and in Podcasting 2.0 compliant apps if you'd like to make a credited submission. Visit engineered.network/create sound bite, all one word, to learn more. There's also a link in the notes. You can follow me on the Fediverse at Chidgey at engineered.space, on Twitter at John Chidgey, or one word, or the network at engineered_net. This was Causality. I'm John Chidgey. Thanks so much for listening.